Hello, my name is Max Liu, and this is my Lab 3 black hole for Physics 2211. These are the things that we're going to be going over today. These are the preview of the results. So for the mass, it's 1.38 times 10 to the 34 kilograms, and the initial velocity of the spaceship is negative 2.3 times 10 to the 8, comma 3.0 times 10 to the 7 meters per second. These are the fundamental principles that will be covered in this lab. So Newton's second law describes the relationship between the force acting on the object and the result of the motion of the object. The second law is used to find the net force of the object as well. And the momentum principle is also can also be broken up into its components, F net parallel and F net perpendicular. And then the formula can be used to find the velocity and position update formula for part 2. So the universal gravitational force allows us to calculate the gravitational force that's felt by a system by a source. So for part 1, finding the mass of the black hole, the system is the black hole and the surroundings of the star. Initial conditions, the mass of the star is 2 times 10 to the 30 kilograms, and then the time is 86,400 seconds, or 1 Earth day. And then the observation time is starting at t equals 0 seconds. Okay, so here's the code. I set the star mass to the value shown in the previous slide, and then delta t set to 1 Earth day. And then line 172 calculates calculates dpdt by taking delta p and delta t, or dividing it with delta t. And then line 179 and 181 finds dpdt parallel. And then line 187 finds dpdt perpendicular by subtracting dpdt from dpdt parallel. And then line 194 calculates the mass of the black hole. Okay, so here are the results for the first part. I got the mass of the black hole to be 1.38 times 10 to the 34 kilograms. And then here's F net, and then F net parallel and perpendicular. And this is the video. As we can see here, as the planet gets closer to the black hole, the arrow gets larger, and then as it gets further away, the F net gets smaller. And the arrows, the orange arrow is F net, and then blue arrow is F net perpendicular, and then the purple arrow is F net parallel. So for part 2, finding the initial velocity of the spaceship. So the system is the spaceship, and the surroundings the black hole and the planet. And initial conditions is the mass of the black hole, 1.38 times 10 to the 34 kilogram. This is the code for part 2. So I set the black hole's mass to the one found in part 1, and then I calculated the net force on the planet by first getting the gravitational force of the black hole on the planet, and then the ship on the planet, and then summing those together to get the net force. And then also calculate the net force on the spaceship, so getting the force from the black hole on the spaceship, and then the planet on the spaceship, and then adding those together. And then I use Newton's second law, the velocity update formula, to calculate the new velocity, and then the position update formula to get the new position. These are the results for part 2. I got this value through trial and error, and as you can see here, the spaceship did not crash into the black hole or the planet. Well, possible sources of error is that I could have run the program longer to get a more accurate average mass of the black hole. So instead of 1 Earth day, we could do like a whole year for a more accurate result. The initial velocity was found through trial and error, so there could be other values that allow the spaceship to be even closer and still not crash into the black hole. The simulation also assumes that no other forces are acting on the system. In reality, there are other celestial bodies that could affect the net force. So what does this mean? How does the net force and its parallel and perpendicular components differ from the rate of change of momentum in its parallel and perpendicular component? So Fnet and dpdt result in the same value, but are not like the same mathematically. The net force requires that you know all the surrounding forces acting on the system for both components, but the change of momentum, you only need know the system's change of velocity and mass. So it's easier to find the change of momentum rather than net force. So for what initial velocity would you need for the spaceship to enter into an orbit? So this is the value that I found for it to be in orbit and not crash into the planet or the black hole. Okay, so in conclusion, in this lab, we calculated the mass of the black hole and found the initial velocity of the spaceship so that it will not crash into the black hole or the planet.